Welcome to our free GRE prep hour for November 2023. I'm Dimitri Farber, and we're going to continue our quant speed strategies series today with some specific work talk about efficient strategy solutions. Um, I'm going to focus mostly on these two areas of my speed strategies that we talk about in a number of other lessons. So partly that's just making sure you know when answers make sense or don't, so you're catching more of your mistakes. Um, and you're avoiding work that you don't need to do. Sometimes this is the kind of thing we can only identify on the back end. After I've done a problem, I say, oh, I did it this way. But actually, now that I think about it, I didn't need to do this step. I didn't need to go this far, or I could have known that my answer was wrong. I think one misconception people have is that when someone is really good at taking the tests, right, when someone's getting a really nice score like our teachers are, that means they're just not really making a lot of mistakes. And I prove that wrong all the time. I make a lot of mistakes, and sometimes I make them on YouTube and then people get to see them forever. Or I make one so bad that we don't want to put it up, right? In tutoring sessions, I put the wrong sign, and this could make me sound very foolish, but I hope it has the opposite effect for you, in that you can say, hey, I get to make mistakes and I can still get a really good or even a perfect score. So a lot of it's about noticing your mistakes before it's too late. And saying, the answer I'm getting doesn't make sense, or it's not what I'd expect. Something is off here. And so that's part of it. It's that sense of recognition. Avoiding unneeded work is partly related to that, because when I take extra steps, those are additional chances to make mistakes. If I rewrite an equation several times when I don't need to, right? If I solve for something that I don't need to find, that gives me a chance to mess it up when I don't necessarily need to do that. But of course, also avoiding unneeded work just makes us faster and more efficient to begin with, right? So what we're going to try to do is look at a few problems today from the perspective not just of what is the answer and how can I do it, but how would I know to do it this way versus that way, and what things can I do when I'm solving to make it more likely that I'm narrowing down the answers, so that even if I get stuck and I have to guess, which is common, that I'm guessing from a more restricted pool of answers, and that if I do finish solving and I've made a mistake, I'm going to notice that there's a discrepancy, uh, and I'm also just looking back and trying to select which of these strategies I like best and how I would think of that particular strategy at that time. Okay. A lot of people, what they do is they do a problem and then they review some explanation, an official explanation, our explanation, whatever it is. They look at the explanation and they say, oh, I understand that. Great. And they move on, rather than saying, would I have done this and how would I know to do this? And I think that's much more important. There will be problems that I understand perfectly, but that I need to review because I wouldn't have thought to do them a certain way. Whereas there might be other problems that I didn't understand very well. But there's nothing much I need from the explanation. I need to figure it out. But once I understand what they're saying, then the strategy I was using it maybe is actually fine. And so it really is going to vary where I spend the time. There will also be problems maybe you don't understand that you don't want to understand. And what I mean by that is you might look at a really ugly problem, a really long, involved, terrible problem, and you might say, hey, this is a problem that I'd probably guess on the test. And I would only do it if I had a lot of time left at the end. And maybe that never happens. And there might be some problems where the right answer is to walk away. And this is true even when you're trying to get a very high score. Even if you're trying to get a 165 quant, you can walk away from a few of the problems and guess, especially if you've already narrowed the answers down and so your guess is, from a reasonable pool. Okay. So let's try some problems. For each one, I'll give you a little time to try it on your own. I'll put up a poll. Target time for discrete quant for everything but the quantitative comparison is 2 minutes, but you might not need exactly 2 minutes, or you could call it a minute 45 if you're averaging that across the whole section. So as soon as it looks like a decent number of folks are done, we'll try this one out together. So try it on your own first. We'll talk. Okay, let me stop you there. It's been 2 minutes. And I want to acknowledge that at this point, most people have not answered. So what I want to encourage everyone to do at this point, whether you're here or whether you're watching this or recording later on, is stop now and write down and commit to an answer. And if you're here, pull me that answer. So even if it's a complete guess, even if you have no idea, put in a letter answer. Let's just see what we get. So I should see everybody answering. And hold yourself accountable in that way, because on the GRE, we're going to want to be in the habit of moving on when problems are taking too long, even if that means guessing wildly. But then we can improve our guesses. And I think that's really important to do to get better at guessing. Okay. So I have a few holdouts. If you haven't pulled in an answer, go ahead and put one in. Okay. So there's definitely some complications here and some possibilities to get in trouble, right? For instance, I might just think that I can square the individual terms and then I would be wrong, right? But that wouldn't leave me too far off. Like, let's say I just did this. Okay, so I'll write in advance that this is incorrect, just so I don't confuse anybody, right? That I'm can really do this. What if I squared each term, each piece, right? So I could say, okay, 3 squared plus or minus, don't get the signs wrong, minus a third squared plus 3 squared plus a third squared. Now this is wrong, but if I did it, I would get, okay, minus a third squared plus a third squared. Those cancel out. And I would just get 9 plus 9 is 18. The good news is that sometimes when we make mistakes, the answer is not there. And the GRE is surprisingly nice, polite sometimes, in that they don't always put the sort of the simple trap answers in as answer choices. I don't want to count on that, but this time they didn't. So I said earlier that I make a lot of mistakes. Well, this is a mistake that if I made, I would be forgiven in a sense, because there isn't an answer that corresponds to 18. And so I'm not going to choose that, and I'm going to know that I'm wrong. And if I have time, I will fix it. And honestly, if I did this, I probably would have time, because doing this really quickly might not take very long. It's wrong, but I can be wrong in this way very quickly. Okay, so let me ask you something. Why is this wrong? What is wrong with squaring each piece the way I did? Okay, I've got an order of operations issue, PEMDAS, right? It's supposed to be parentheses before exponents. When I square something that's multiplication, because multiplication and exponents are kind of the same operation in a sense, right? An exponent is repeated multiplication, that distributes. So if I have xy squared, I can write this as x squared y squared, right? I can still say I'm following the order of operations, but what I'm saying is that those turn out to be the same thing, and you could prove it. 6 times 6 is 36, but so is 2 squared times 3 squared. However, if I have x plus y, I have this other pattern that emerges. I have to, as they say, FOIL it out. And I get x squared plus 2xy plus y squared. And if this is something that you don't recognize, or let me say even better, if this is something that you don't have memorized, then address that immediately. Put this on a flashcard. You want to know this one, x plus y squared. You want to know x minus y squared, and you want to know x plus y times x minus y, the 3 quadratic templates. And those are everywhere on the GRE. Expect to see them, have them memorized for sure if you haven't already. So I can do this out. But as you can see, that would be a bit of work here. So I might want to consider, how wrong is this answer of 18, right? Can we agree that 3 minus a third squared is pretty close to 3 squared? So I shouldn't be like drastically wrong. And if I get an answer like E, I've done something wrong, right? In fact, E is 81 plus 81. This is if we accidentally square again, right? We kind of square 3 and then we square it again to get 81 and double that. Why would we do that? I don't know. I've managed to recreate it before when I was sort of playing around with it. And I was like, oh, if I did this, I might start doing, oh yeah, no, don't get 162. So that's too big. I know 36 is not 18. It's double, right? How about these other ones? Roughly, what's D equal to? 53. Yeah, okay. So I've got 150 divided by 3 plus 14 divided by 3. Yeah, something in that neighborhood. It's a little over 50, right? Um, okay. And then so that's going to be too big. And then these other ones, one quick way I could do this, of course I have a calculator if I want to, but a quick way I could do this is to say, hey, divided by 9 will be a bigger answer than if I divide by 10. So this will be greater than 12, and this will be greater than 16. And if I had to guess, it's hard to know, like, because I don't know if my answer should be less than 18 or more. But either way, B would fit because B might be more than 18. I don't know, right? It might be a little less than 18, but it's in the neighborhood. So can we agree that B is a kind of a sensible guess at this point? I'm not saying we've proven it. We could be wrong, but can we see how we might get there just from this point if we were short on time? And then if we have the time to confirm, we can confirm, but then we know to expect this. And when we know, that if we get an answer really different, something is wrong. So one way that I think is maybe kind of a hard way to do this would be to apply this. And sometimes partly what I included this for is sometimes what I think of as like the clever, savvy approach is actually not the simplest way to do the problem. So if you know this and if you're clever about it, you could say, oh, this is like a formula. I could say x squared plus 2xy plus y squared is what I get when I square something. And then I know if I have x minus y squared, I get x squared minus 2xy plus y squared. And so I could recognize that. And if my x, is, so to speak, is 3 and my y is 1/3, I could write this whole thing out as let me do it this way. Do it this way. I could do the individual pieces and I'd get 3 squared minus 2 times 3 times 1/3 plus 1/3 squared. But look what a mess this is. And look how easy it would be for me to be wrong at some point. And then for the other part, I'll have 3 squared plus 2 times 3 times 1/3 plus 1/3 squared. It's a bit of a mess, right? And I'm running off the screen. That's how bad it is, right? I would rather not do this. If I do, and I catch all my exponents, if I do, then hey, this minus part and this plus part will cancel out. And what I'll see is I'm going to be more than 18. And we can look at how we might have predicted that a little bit in a second. But we'll be more than 18, and so we'll have 9 plus a ninth plus 9 plus another ninth. So it has to be 18 and 2/9. Now, if you do that out, 18 times 9 is 162 and 2 more is 164. I can find B, but I don't actually care because it has to be B. It's not C. A is too small. It's going to have to be B, and I don't want to do that work. So I've already done too much work here. Can we agree? This is more work than I would like to do on this problem. I think it's useful from a study perspective to see these patterns and go, oh, look, these cancel out. And to even say, hey, maybe I should have predicted the answer would be a little more than 18. Because if I know before I do the work, that I'm going to get 3 squared and 1/3 squared, whoops, and also 3 squared and also 1/3 squared, but then also I'll get a middle term that's negative here and a same term that's positive here, then without doing all this, I could say, oh, the middle terms are going to cancel out. It's like, let's say I know in advance I'm adding these two together. Then I'd say, oh, these cancel out, and I'm going to get 2x squared and 2y squared. So someone who really knows these in and out, like it's in their DNA. Someone who really knows these that well might just glance at this and say, oh, I'm going to get 2 of this squared and 2 of that squared. I'm going to get 9, and I'm going to get 2 of 9. I'm going to get 2 of 1/9, and they would be done. But for most of us, we don't necessarily want to do it that way. So yeah, Nafreet's asking a really good question, which is, what happens if there are variables? Because of course, what some of you probably did, I honestly hope some of you did, is none of this and just found out what this was. Did anyone do this? Anyone just square 3 minus a third and square 3 plus a third? And you might be wondering why we're even talking about all this other stuff. Because I could simply say, 3 minus a third, that's 9 thirds minus 1/3, that's 8 thirds. And 3 plus a third is 10 thirds. And here's where it's like, I don't know, what's the opposite of the revenge of the nerds, the revenge of the non-nerds, where you're saying, look, I didn't need to do all this weird algebra to retrieve. I just found out, even on my calculator, what 3 minus a third is, and I squared it, you know? But then I'd go, oh, so this is going to be 8 thirds squared plus 10 thirds squared. And then I can just square the pieces, right? That's going to be 64 ninths plus 100 ninths. And oh my goodness, I know what 64 plus 100 is. I do not even need a calculator to add 100 to something, right? Oh, well, that's easier. I mean, can we agree that that's just a better way to do the problem than anything I was showing you earlier, right? But I hope it wasn't wasting your time for a couple of reasons. One is this is a process that we're doing when we review problems. If we got a problem right, if I got it right doing all that algebra, now I might look back feeling a little silly, like, why did I do that? I could have just done these. So one moral of the story then is, if the problem is about simple numbers, then algebra is often a waste of time, right? So one thing I'll say about algebra is one of the most important inventions in human history. It's hugely important, and it allows you to create all these algorithms and programs, and it allows you to extrapolate about things where you don't know all the information. But when you do know the information, it's silly, right? If I say I drove 50 miles an hour for 2 hours, how far did I go? You're not going to write down an equation with some variables. You're going to go 50 twice, that's 100. Done. You're not going to, and you shouldn't do any equations, right? You should just simply say, you did 50 and 50 again, that's 100. And writing a bunch of math down would be silly. So when we have the numbers, let's use them. But yeah, if we have variables, then we'd have to do it. So let's say it had been something like 3 plus q. It looks like it could look like a 9, right? 3 plus z squared plus 3 minus z squared. Then it might be really useful to recognize either all the stuff we wrote out before, or to recognize, hey, the middle terms are going to cancel. In general, I'm going to have something of the form, 3 plus 2 times 3z plus z squared for one of them. And I'm going to have, this would be 3 squared. And I'm going to have something of the form 3 squared minus 2 times 3z plus z squared for the second one. And so I can recognize two things. One, that the middle terms cancel out. Two, that I have a little bit more than I would without the minus 1/3 and the plus 1/3. I have a little bit more than if I just squared 3, as long as, as long as I'm adding a positive thing in. Of course, z squared is going to have to be positive, right? Unless it's 0, and then it doesn't mean much. Okay. And so we'll have something same form, 18 plus 2z squared, which is what we had here. It just happens that here our z was 1/3. Right? So for something like this, I need the algebra, I need the formula, because I'm dealing with an unknown. So use the algebra, make sure you're comfortable with it. You wouldn't want to take away from this. See, I don't need all that stupid algebra, so I'll just tune out all the stuff you said before. No, now we need it. But on the actual problem as written, we didn't need the algebra. We could just find out what 3 minus a third is. We can find out what 3 plus a third is. But even more to the point maybe is we didn't even need to do that, because once we saw that it was in the neighborhood of 18, even though 18 is the wrong answer, that still got us the answer, because it's not that different from 18. It'd be like if someone earns $1 million at their job, what does their take-home pay look like? Well, they probably are paying some taxes. They ought to be, if they're making $1 million, and they're probably paying some this. But we know it's closer to $1 million than to, say, 10,000 or to $1 billion. It's certainly not going to be more than $1 million. And so we know, okay, $1 million take home is going to be max $1 million, probably a bit less, not drastically less, and we're going to cross out all the wrong answers, right? And so same kind of thing here. I can know that my answer is not that far from 18, and that's really useful to be able to do. Okay. That all right? Questions there? You might have found this problem not that bad. Cool. But notice that even a problem that you didn't find that bad, there might be ways to get lost in it, but there are also things you can learn and study from it, even if you got it right. Maybe you just really quickly, banged out the numbers here, or maybe you just did it on a calculator and then just saw which of those equaled that number. That's fine. Right. But you still might look at how you'd get rid of some of the wrong answers, how you'd work out the algebra in cases where the problem is a little bit different. Okay. Let me give you another one. Same deal. I'll give you some time to work it on your own. Pull it in when you're ready, and then we'll discuss. Okay, so there's 2 minutes. So again, put in your answer if you haven't already. Okay. Okay. So this is a little bit intimidating, I think. And I could definitely, again, do some algebra here. For which of the following positive integers is the square of that integer divided by the cube root of that same integer equal to 9 times that integer? So one thing to watch, and this is the same thing you'll see in, say, reading comp, when they say something like that integer, what are they talking about, right? In a reading comp, they might say, that principle has been followed thoroughly here. And you're like, wait, what principle? Wait, hold on, let me go back. But they say, notice over and over again, that integer, the same integer, for which integer, right? So they're just saying, find a number where you do all these things with it, it's true. So there's only one unknown that we're dealing with. Thank goodness, right? There's not several. And which is maybe why they can have an answer. If I was going to take the square of one integer and divide by the cube root of another integer, then maybe there'd be a bunch of different answers that I could get, right? But if it's one same number, then it makes sense there's only one relationship. That's important because if this were, say, a quantitative comparison, and they were having like the answer, maybe quantity B was 16, then you might say, hey, could it be more than 16? Could it be less than 16 or equal to 16? Or does it always have to be less, right? So, or, whatever we call it, n, whatever that number is, if it were quantity A. So if you chose on this, C, the answer to C, that would be C on this quant comp as well. You'd be saying they're equal. If you chose D, you're saying that no, quantity A would be bigger every time. But if you thought, hey, it could be either, right? Then you go to D and say, hey, it could be A is bigger, B is bigger, equal, whatever. Okay, so we can certainly set up some algebra here. But I might also think about some limitations here. What's something that I can know has to be true of this integer if it's going to fit what they're saying, right? And I don't mean like what's the answer, but they're saying that I'm going to take this integer and I'm going to square it, but I'm also going to take the cube root of it. What does that tell me I should look for in the integer? I think this is one of the clues here. If I'm going to take a cube root of it, I should be able to take a cube root of it. So it doesn't necessarily automatically, that's a really interesting point about 9. Let me come back to that. So it doesn't automatically tell me, what kind of number it is exactly, but it seems like it ought to be a perfect cube, right? In other words, it should have a cube root, because if I have something involving a non-perfect cube, like let's say I try to take the cube root of 4. I don't know what the cube root of 4 is, right? It's more than 1 and less than 2. It's 1 point something, but I don't know, and maybe I don't want to know what that is. And so how is it going to turn out that that's going to be fitting into being 9 times something? And so I could strongly suspect, and if I'm wrong, but I could strongly suspect that it's got to be either 8 or 27 or 125. And I would suspect that it is not A or C, because you can't take the cube root of those, right? There's not a number times itself that equals 4 or that equals 16, at least not an integer. And we know we're dealing with an integer, right? It didn't say that the cube root was an integer, but we can strongly suspect it if this is going to work out, especially on a nice 2-minute GRE problem. Okay, so that leaves me with 3, and this gets us to a really important principle, which is working backwards. Especially if you've got it narrowed down, right? You could just say, hey, only 3 answers have integer cube roots. Let's just test the middle one. And if it works, we're done, right? Now, I don't always test the middle one because I don't always know which way to go. But if I think it's too big or too small, I could go with there. So we could test any or all of them. But if I test the middle one, I'll say, okay, the square of the integer. Oh, I don't know what that is. 27 squared. That doesn't sound that fun. Okay, divided by the cube root of the integer. Okay, I do know that. Equal to 9 times that integer. Now, before you get too excited about finding what 27 squared is, don't even get out your calculator. Yes, you have one. Don't get it out. What should you do at this point? Start simplifying, right? One way would be to break this down to 27 times 27 and divide by 3. But I think even easier, just to multiply this 3 to the other side. Because now I have, hey, is 27 squared equal to 27 times 27? That's pretty much what that means. So yes, D is my answer. I don't need to find out what 27 squared is. I don't need to do a lot of math. I don't want to waste my time. I don't get any extra points for doing all the math and having the numbers on my page, right? I just want to move things over so I can cancel. But in this case, I might even rather not cancel. I might just rather, I'm canceling the denominator, right? But I'd rather not like break numbers down and say, hey, 27 times 27, and so divided by 3, that's 9 times 27. Then that would match too. But I think this is even easier. Okay. Whereas notice if I had tested 8, I don't need to test them both because it's not a choose all that apply. If this were a choose all that apply, I would have to test B. I'd have to test E because it could be all of the answers, right? But if there's just one, then I know I'm done. But if I had tested 8, I'd say the square. Hey, actually, I know what that is. Divided by the cube root. Hey, is that equal to 9 times 8? And Well, no, right? One's 32 and one's 72. I could also just know that, hey, the right-hand side has a 9 in it. So this doesn't work. Specifically, if I were testing several, how would I know that this is too small? I might recognize that multiplying by 9 made the right bigger than the left. If I go up, the 9 should matter less. And that's a general principle you can use when you're testing cases, when you're working backwards, that if there's some fixed difference, right? Like I have to pay $200 per paycheck for medical and dental, or I have a 2 mile handicap, when we start racing, you start ahead of me by 2 miles or whatever. That matters a lot when the numbers are small, right? If we're not racing for very long, if I'm not getting paid very much, that makes a very big difference. And as the numbers get larger, those fixed differences matter less. And so if I went the other way to 125, I definitely don't want to know what 125 squared is. And then I have the cube root of 125. There's no cube root key on your calculator, but there's a square root key. Equals 9 times 125. Then I'd see the opposite thing happens. I'm going to have the left-hand side be bigger, right? Even if I move that 5 over, it's going to be, hey, is 125 times 125 equal to 45 times 125? Now the left wins because the 125 is so big it dwarfs that 9. And so that's why D works out. And then 9 is not a coincidence, as one of you pointed out. We might expect to have a multiple of 9 because how else am I going to get a 9 in the number, right? So yeah, and someone else is saying the same thing. Could I expect that it has 3 as a prime factor? Yeah, you could expect that. You could expect that, right? And in fact, that's, if we think about this in algebra terms, you might actually prefer this algebra solution in this case, because they're not giving us hard numbers to work with. We went around that by putting numbers in from the answer choices. But I could also say, hey, I want an integer squared. And I think it's good to practice this stuff, especially if it's uncomfortable for you. And I want the cube root of that integer to be divided by that. And I want that equal to 9 times the integer. And what I can see already from here, I hope, even before I do any math, is that 9 has to be a factor of at least the square of my integer. And that's where someone said, maybe I should have 3 as a prime factor. Because if I know that like x equals 9y, then I know that 9 has to be a factor of x. X is 9 times something. It's in my times tables. And 9 might be, y might be like 0, and x could be like 9 times 0, but it's still in my times tables. If I know that x squared is 9y, then maybe x isn't a multiple of 9, maybe it's just a multiple of 3, and x squared is a multiple of 9. We don't know, but we at least know it's a multiple of 3. From here, what would my next step be? Someone's asking the difficulty. This maybe in the middle. It's not the easiest problem for sure, but I think because it has nice concrete answers, that keeps it from being as bad. So from here, it's helpful to know that a cube root is a third power. So I could say n to the 2 divided by n to the 1/3 equals 9n. And in fact, I could even kind of do this. There's various ways you could do this, but one way to do it is 2 minus a third. So n to the 5/3 equals 9n. And then I can divide by n. 5/3 minus 1 or minus 3/3 is n to the 2/3. So if this is sketchy exponent work for you, then that's all the more reason you might not want to do it this way, right? Because it is a lot of work with like flipping, and it's easy to make a mistake in here. So talk about avoiding excess work. You might say, hey, this is nice algebra, but it looks like more place for me to make a mistake. And then the key move here is if I don't have a way algebraically to do this, I'd have to just say, hey, which makes sense here? And the 27 might make sense. You can see, hey, there's something going on with 9s, right? And D is my only multiple of 9. But if you want, you can also raise both of these to the 3/2 power. And that might not be something everyone realizes they can do, but it is something you can do. So I can raise this to the 3/2 power, and that cancels the 2/3. 2/3 times 3/2 is 1. So I'd have 9 to the 3/2 power. I can square root it and cube it, or then cube it and then square root it. I'd rather do the former. So I'll do 3 to the 3rd is 27. So there's a lot of little like exponent moves. And I hope that if that wasn't something you knew how to do, that you picked up some steps from this. And if you're looking at me like, it's worth reviewing that so you can do this. But is this the right way to do it? I mean, it got us the answer, but I think the other way might be easier. Narrowing down, seeing what makes sense, recognizing the properties that are going on, recognizing that we should have a multiple of 3, having some expectations of what to look for in the number, and then just trying what you have rather than always trying to do the algebra. So it's nice to do this, but I wouldn't argue that this is the right answer. And in fact, I would argue that for most of us, it's not a very wise way to do the problem because I'm more likely to be wrong. And I think people really emphasize the wrong thing on this test a lot of the time. People emphasize, do I understand the problem? Am I able to do it? Instead of, was I guaranteeing myself, or at least coming close to guaranteeing myself, that I'm doing the best I can to be right? Was I avoiding unnecessary errors? Was I catching the mistakes I make? And I think people focus too much on, when they're doing it, do I know how to do this kind of problem? If so, I'm going to do it no matter what, even if it takes me 5 minutes, and even if I get stuck. And when they're reviewing a problem, they focus on, do I understand it? Great, then I'm done. I don't need to review anymore. Or if I don't understand it, let me like break my brain on it until I do. And I think that's incorrect. I think it's really incorrect. On the test, you want to focus on, is this something I can practically do in the time allotted? And what can I do to ensure my accuracy if I am going to do it? If I'm going to guess on it, are there any steps I can do to ensure my accuracy of my guess? And then in review, I want to say, did I do this problem optimally? And what would I need to recognize in order to do that? Are there other solutions available to me? Are there things I want to remember or notice next time, or the things that could jump out at me? Maybe there's just a rule I didn't know, and there's no fault of mine. I just didn't know the rule. Okay, so now I'll know the rule, and this problem will not be a big deal. So I'm not maybe so concerned about a problem I missed. Whereas another problem, maybe I knew all the rules and I still missed it because I said that 5 times 4 is 40. Well, wait, why did I say that? Was I skipping steps? I think a lot of people are going too fast at the beginning. They're rushing at the beginning. They just want to get to the answer, and they end up missing way more questions than they need to. Okay. Other thoughts on this before we move on? I'm going to give you a pair of quantitative comparison questions next. Now, quantitative comparison, some difference of opinion on exactly how long it should take. On the newest versions of the test, the shorter GRE that we have now, you have average, like, it's similar to before. You have an average of 1:45 per question, but the way that usually works out is that you could plan, if you plan for 6 minutes for the first 5 quantitative comparisons you see in the 15 question section, that would give you 2 minutes each for the discrete quant questions you see. And so if you want 2 minutes per question on the regular multiple choice or the fill in the blanks, then you want to have only about 1:12, 1:25 for the quantitative comparisons. If you can get through the discrete quant a little faster, you can have a little bit more time for the quantitative comparisons, but not much. So having said that, I'm going to give you 2 quantitative comparisons, and I'm going to see if you can get through them in 2.5 minutes. And so that's what I'll want to check in. So what I'll ask you to do, though, is on these 2, pull in for the top one when you are done with both of them. So when you're done with both, pull in your answer for the first one. So I'll stop you in about 2.5 minutes if I don't have answers yet. Just as a reminder, the answers for these are out of A, B, C, D. A means quantity A is always bigger. B means quantity B is always bigger. C means they're always equal. And D means there's not an always, that it depends on what you pick, right? That it can vary. On some, you could tell right away that it will be able to vary, but you just won't know if that variation affects whether A or B is bigger. You might just have different numbers that are all bigger. On others, you could tell that it can't vary, and then the trick is just which out of A, B, C it is. Okay, so give these a try. Okay, so that's 2.5 minutes. It goes pretty fast. Go ahead and pull in your answer for the first one, even if you're not sure. Again, A, B, and C correspond to, this is always true. A is always bigger, B is always bigger, C is always, or they're always equal. There's no C. C means they're both equal. And D means it varies. Okay. Both of these problems can be seen as a similar type in one way, which is their optimization problems, where we're saying, hey, there's a fixed quantity in B. Can I exceed that fixed quantity or not? And this is a really common pattern we see. It's so common that one of our strategies we call cheat off B. But it's often really an optimization thing, right? Because we're saying, okay, if 30 is like an interesting quantity, if 25 is an interesting quantity, can I exceed that, right? And so, I mean, think about like a real world thing. I might say, what's bigger, the age of a legal voter or 18? So 18 is not a random number. In a lot of places, 18, you're considered an adult, you can vote, but I haven't said where. So I might say then, okay, so it's an optimization thing. Are legal voters always 18 or older? Or is there any place in the world or in the country or whatever they're asking about where you can vote legally below the age of 18? And if there is, then I can get, a different answer, right? You might also argue in that case that, wait, hold on, but in the US, you could be 18 or more than 18, so it's already D, right? So it just depends on what they're asking, right? So here, I'm going to say, I'd like to find out like what maybe the biggest possible area is to see if it exceeds 30. But I can certainly start by just finding any area at all, okay? And perk up if this is not familiar, because I think this is probably one of the most maybe the most important thing someone could tell you about GRE math, okay? Which is that anytime you're testing cases on quantitative comparison, you can always get it down to 2 with just one case. You can always get it down to 2 answers with one case. And that's one reason these can go really fast. So let me show you what I mean. Someone give me a possible rectangle with a perimeter third of 20, any rectangle at all. Just what could the dimensions be of a rectangle if its perimeter was 20? Perimeter is just the sum of the sides, right? So the sides have to add up to 20. So what could the sides be? We're not too chatty. All right, well, let's do 6 by 4. Okay, so if I have a 6 by 4 rectangle, the perimeter is 20. What's the area? 24. So in this case, the area was 24. That means in this case, B1. So here's the part where I said perk up, make sure you have this, make sure this is like automatic in your DNA, whatever. What answer choices then are impossible? If 30 can be larger than the area, 30 can be larger, what answer choices are impossible? Looking down my line, A says quantity A is always bigger. Well, quantity A wasn't bigger this time, so how can it always be bigger? B says B is always bigger. I don't know if that's true, but it was bigger this time. C says they're always equal. That's not true. They weren't equal this time. And D says it depends. Well, that I don't know. I would only cross off D if I knew that this could not vary, right? If I knew it was always the same, but I haven't proven that with just one case. Doesn't mean the answer is D, I just don't know. And so in general, one short way of saying that is that when you get a result, it's either always that or it's D. When you test cases, when you test a case, the answer is either always that result or D. It's a 50-50, right? So here we got B, so it's either always B or it's D. Okay, so now what we'd say is, can I improve this? Can I pass up, pass up 30? And if no matter what I try, I can't pass up 30, I'll pick B. It's hard to prove that because how do I know I've gotten the biggest possible area? might be able to do that. So sometimes I feel like I'm guessing, and that can happen. Whereas if I can find one bigger than 30, then I know I'm not guessing, because I'd say, okay, if I can get 36, then of course it's D, because I can get more than 30 and less than 30. Okay, so that's really important to memorize. Just make this part of your toolkit for quant comp for sure. So I could try different numbers. And what I might see is which way the numbers are trending. I don't have time to test a whole lot of numbers. This is meant to be done in a minute and change, right? So let me make my my figures a little smaller, but I'll just draw it like this. What if I draw, not to scale, of course, just trying to make room. What if I draw a 7x3 rectangle? Well, if I do 7x3, it's getting smaller. And you could maybe even do some of this in your head. 8 and 2, 16, 9 and 1, 9. And in fact, one thing that's really useful to realize is that the area could get as close to 0 as I want. Of course, I can't have a rectangle with area 0, because then it's not a rectangle, it's a point, right? But I could get as close to 0 as I want. Imagine the area, like imagine one of my hairs was a rectangle. What's its area? Well, no matter how long it is, it's very close to 0, because it doesn't just enclose much space there. And so as the numbers get farther apart, the area gets smaller. And notice that if I try to go the other way, the same thing. If I flip the length and the width, doesn't matter. So what does that mean? I have to bring them closer together. And in fact, this is an optimization principle that you want to memorize. When you're trying to maximize area for a given perimeter, the closer you can get to a perfectly symmetrical shape, the better the area. So ideally, if you have some fencing and you want to fill, cover the most land, you make a circle. Right? If you can't make a circle, you make a polygon with lots of regular sides. And if you can't make a polygon, you make a square. Right? You want it as symmetrical as possible. And so if you do a square, that would be 5 by 5, 25. That's the max. How can I know for sure it's a max? Because if I start to I can't bring them any closer together. And if I make one bigger, I'm going back toward the other way that I already had. 6 and 4, or 7 and 3. Even if I make them non-integers, 5.5, 4.5, that will be more lopsided. It'll be less than 25. So I can't exceed 25. 25 is the max. A sneakier question might have made 25 quantity B. Of course, then you can have 25 and you can have below. Or maybe a sneakier question would have done 26. But this is that same idea. It's like, hey, 25 is the maximum. So B always wins. And we've actually proven it, so we can feel pretty good getting rid of D. Okay. Questions on that? Okay. Let's re-poll for the second question. Go ahead and pull in your answer for the bottom one, the arithmetic mean one. So once again, what I want to stress on this one, and if you didn't get a chance to finish it, or if you don't feel like remember that you can't win if you don't play. And this is a 1 out of 4 multiple choice. So even if you have no idea, even if you couldn't read this, even if it were written in a language you've never seen before, if you just put in a letter, don't pick E, that's not an answer, right? If you pick one of the letters, you will have a 25% chance of being right just off the bat. And if you can test in a single case, you're going to have a 50% chance now, as long as you test that case correctly, right? So let's see what we're talking about. This is another optimization one, because they're basically asking us to optimize the range of ages. Could the people be more than 25 years apart? Could they be exactly 25 years apart? Or could they be less than 25 years apart? That's what I really wanted to test. Maybe no matter what I do, the oldest person has to be at least 30 years older than the youngest person, right? Then A would have to be bigger than B. Or maybe whatever I do, I just can't get the ages that far apart. Then B would have to be bigger than A. Maybe it's always 25 no matter what I do. Then it's C. Right? But I want to be able to prove something by testing some cases. So thinking about how before we could minimize the rectangle as skinny as we wanted, right? So if I wanted, I could have had a rectangle like, it's not to scale, but imagine one that's got a length of 9.999 and a width of 0.0001. Okay, that would have an area very close to 0, right? Not 0, but a tiny fraction of 1. And so we know we can get a lot less than 30. So the same thing here. If I want to minimize the range of their ages, what can I do? Well, what's the easiest way to minimize the range in people's ages? Same way I could minimize the range of my employees' salaries. Pay everyone the same. Make everyone the same age. So if I have 4 people who have an average age of 18 and none of them are older than 30, can you agree that I could just make them all 18? So right away, I'd say, hey, there, the range is 0. The range is just the difference between the biggest and the smallest. The range, there's no range, right? Well, the range is 18 minus 18 is 0. So once again, I can make B win. So I'd get rid of A and C again. It can't always be A. It can't always be C. Now my immediate job is try to make the range 25 or higher. I don't want to just get another answer. So I wouldn't want to do something like 17, 18, 18, 19, because then my range is just 2 and that doesn't help me. I already know that I can make the range small. So I don't want to do this. I could, but it doesn't serve me in any way. So instead, I want to try to maximize the range. How would I do that? Make them far apart. But I need the average to be 18, right? So what I could do, I could mess with all the terms, but maybe I'll leave the 2 people in the middle at 18 because I don't really care how old they are. And then what would I do to the people on either side of 18? Right? It says none of the people are older than 30. Let me make one of them 30. If this person is 30, that's 12 more than the range. All right, sorry, the range. That's 12 more than the middle, the middle terms here, which are equal to the mean. So what would the first person's age have to be? You can verify all this with calculations, right? It would have to be 12 less. You're close. Yeah, it would have to be 6. Right? So the idea is, if I want to make the oldest person as old as possible, I'd have to make the youngest person as young as I can that still balances out. 36 divided by 2 is 18, right? And so if you didn't realize you could do that, you can. If I have a bunch of things that average to 18, then I can add in whatever I want as long as those also average to 18. It's like if you've been averaging 40 hours a week all year and you want to keep doing that, you don't have to work exactly 40 hours every week. But if you have a week that's 30, you can balance out with a week that's 50, or a week that's 30 and 2 weeks that are 45, but they have to balance out. For every over, there has to be a corresponding under. And so here I could say, all right, now I can get a better thing. Now this still doesn't beat 25. And at this point I might figure, hey, I'm done for. I made them as far apart as I could, and the range didn't beat 25. Is there anything else I could do to expand the range? Could I make someone any younger than 6, let's say? So let's think about this. What if I wanted to make one of the people, and this is also interesting to think about. Let's say you really quickly decided that B was the answer. You got one case and you were good, or it just seemed obvious to you. And then let's say you check the answers later and you got it wrong. One way to say is like, oh, well, I just messed up, right? But another thing is to think of what kind of thing could I still have tried? Um, okay, so I can make one of them is a little small if I correspond with a larger number somewhere else. Yeah, that's what some of you are saying in the chat. So if I do, let's say I just started with what I want. I want to get a range more than 25. So what if I just did 0 and 30? Could I put 2 numbers in the middle so it still averages out to 18? Could I do it? I could think about it. And this is often what I do with means, honestly. If they say the mean of 4 terms, that's going to equal the total divided by 4. And that's equal to 18. What I'll instead write down is just the total. When they say the mean is 18, I'll instead write total equals 4 times 18 is 72, because that's often more compact and easier to think about. So if the total 72, then I could say, oh, let's see, I need 42 more. I'll just make these two 21. No one said they had to be 18, right? I was just doing that for ease, right? But I don't want to be seduced by my own numbers and think it has to be that way. Oh, look, the range can be 30. I don't want to mess with like negative numbers. What if the youngest person is -4? No, you can't be -4, right? We do have to have real world thing. And you might say, but can someone even be 0? You know, what if they're a baby? Do you count them as 0? Thankfully, it's not dependent on that, so we don't have to worry. And that's really common with GRE problems. If there's some edge that seems poorly defined, it's because the edge itself doesn't matter. It doesn't matter if the youngest person in the world is 0, which they are technically, or 1. If they could be 1, they'd still get a range more than 25. So it doesn't depend on whether you consider a baby 0 years old countable or not, which technically I think they are. So this gets us D. We know it's not B because sometimes A is bigger. And that's our process on these, right? So we're testing cases, but I hope what you got out of this, if nothing else, the minimum is that anytime I get a single case, it's a 50-50 shot. And that's one way to get through this quantitative comparison section a little faster. It's either that thing that you got or it's D. And then you actively try to get an exception to that thing you got before. You don't just want to choose random numbers and make the range 2. You say, hey, I got a number with a rectangle that's close to 30. Can I get it any bigger? Here, I got a range that's really low, like 0. Okay, how big can I make the range? How far apart can I spread these? And if I have something like 30 and 6, can I spread it even further? I can't make 30 bigger, so can I make 6 smaller? What do I have to adjust in the middle to make that happen? Okay. All right, folks. Well, I will stop there. I hope this was helpful to you. I hope you continue to review for efficiency. You can check out some of my other sessions where we talk about a lot of these speed strategies. If you want to check out one of our classes, oh, this says GMAT, sorry. You can check out a GMAT class too. GMAT's changing, interesting stuff. But haha, GRE, you can check out any of our classes to see more sessions available to you. And you can also check out our YouTube channel and see other videos like this. All right, folks. Well, I hope this was useful to you. And anything else I can do, stick around and ask. I'd love to talk to you. Other than that, I will see you all at another session if you'd like, or I'll wish you best of luck with your test. Thanks, everybody, and have a great night.